Hello everyone, it's 7 p.m., so I think we can start our lecture. So, welcome to the fourth day and the first day of our second part of the workshop, which will be solving the max cut problem for graphs using Grover's algorithm. And for that, we're also going to introduce a new framework that we'll be working in, which is Circ. It's an alternative to Qiskit. And first thing I will do is show you the notebook where we'll just revise things. It's very similar to the notebook um, where we revised Qiskit. And I think the upside of it is that during this workshop, we're not doing that much advanced programming. We just need the basic commands to create registers, to be able to operate gates, and to be able to measure and see our states. All right, we're importing circ using the import circ command. Next, we also have to create qubits. There are two different ways. First of all, we can name qubits. So assign a qubit to a variable. Here we have qubits that is a source and a target, so naming it S and T. Those are the variables, but the names will be put as an argument as a string. So here it's source and here it's target. So we're doing circ dot named qubit function and then the string of our name. And we can simply print the variables which will print the names. The other way is maybe a bit easier if you have more qubits, and this is to create a qubit that is located on a line and where each qubit will be identified by its coordinate. And in this case, we also have a variable, and we will have the circ and then line qubit, so the qubit on a line, and assigning the x coordinate. So this is not the number of qubits, but it's the coordinate of the qubit on the line. And if we return it, we'll simply have q of 4. So that's qubit, that's the coordinate. Now we usually want to create more qubits, and in that case we will create a list. And we'll operate on those just as lists, which should be convenient for us knowing Python. So first we're creating QList, and then we have a function line qubit, and so this is the same as the line qubits approach, but here we're putting range and 4. So this time it is as if we created a line qubit for qubit 0, 1, 2, and 3, similarly to how range works. And we can just print QList2, which will be our third qubit on the line. And also, if we want to name our qubit something specific, we can do it. Simply putting commas and then using the same function. Now, we have our qubit, so we need a quantum circuit. And for that, we're using simply the function circuit. So circ.circuit. And we're naming our circuit. Of course, next thing we need to have our quantum algorithms are gates. And gates are applied to qubits as operations, which is similar to how we work on it when we're doing mathematical operations. And the operations are appended to the quantum circuit. So it's as if we're appending the list of our operations. And yes, qubits do not specifically belong to the circuits. And first we need to import the gates. The names are pretty self-explanatory. X is the X gate, Z, Hadamard, controlled X, controlled Z, swap, and double controlled X, so the Toffoli gate. And what can we do? First, we can append our circuit with the gate X, and we're doing it to qubit 2. Now, we can also apply the Z gate in a very similar way. The Hadamard will apply to qubit number 3. We're applying C0, and then the first qubit you write is the control, the second is the target.
Excuse me.
Yes?
When you mean qubit 2, I think you mean qubit 3 because they are indexed from 0, right?
Yes. I mean, if we're talking about which one it is from 0, yes, but here the names are just used in the comments and in the general explanation. But yeah, I think it will be clear if I just use which qubit it is online. All right, so when we have control Z, it works in a similar fashion. Swap also, so well, here the order won't matter. In control Z also it won't matter. And if we have a double controlled, then the last qubit is the target and the rest of them are controls. So let's see what we have. We can print the circuit and we have our qubits here. And the nice thing about it is we can forget about the Qiskit order, at least until we write in Qiskit again. So I hope you're glad about that. I'm sure I was when I first learned Circ. You don't have to turn everything around in your head. And this is the operations with it. So the X gate Hadamard in Z, controlled X, so the at here is the control, the double at is the controlled Z, the double X is swap, and then this is the Toffoli, with the at being the controls and the X being the target. We have our first task, where we want to create a quantum circuit with 10 qubits, apply H gate to qubit 0, and apply 9 CNOT gates, where qubit 0 is the control and qubit I is the target. For I, from 1 to 9, it's a very similar task to the one we did when we are revising Qiskit. So there will be 5 minutes for that, so until 7:15. Seems most of the people are ready, so we can proceed. So we're importing circ, and then from circ we're importing the Hadamard gate and the controlled NOT gate. First, let's create a list using the line qubit function. And we're using range to create 10 qubits. They will be numbered from 0 to 9. Next, we're creating a circuit. And applying the Hadamard. So we're using append here. We want to use Hadamard. And here's the specific users that we're using Hadamard on QList 0, because we need to apply it to qubit 0. Then let's use a loop. 1 because we want to exclude 0. So it will be 1 to 9, including 9. Controlled NOT gate. On first of all the 0 qubit as the control. And the ice qubit as the target. Then we're going to print the circuit. We applied the Hadamard gate to qubit 0, and then we applied the CNOT gate 9 times, where the 0th qubit was in the control each time, and the targets varied. All right. You can think about what the solution to it would be, what is the state that we would get. But I can proceed. So similarly to Qiskit, sometimes we want to make our lives easier and apply the same gates to multiple qubits at once. And we have to use the keyword for on each for that. And we're using the star to unpack a list. So from a list, we're just unpacking it to each of the elements in this list. So we're creating a circuit. Next, we're using the line qubit range 4. And we're appending the Hadamard on each qubit with unpacking our list. And when we print the circuit, we see that the Hadamard has been applied to each of the qubits. If we want a controlled version of a gate that is not included in circ, we can do it just using controlled by. So first we're putting the gate and what we want to apply it to, and then on it we're using controlled by and putting the controls then. So here we had Hadamards. It's the same circuit we're working on. And we put the target first, so the target is qubit 2. And then the controls are all of these. Now, we can also first define the operation. So here it will be controlled, controlled, controlled Z. So it will be Z controlled by 3 qubits. And then we can append the gate that we just created, also by unpacking the list. Here using also the range. You don't have to use the 0. And then we're printing the circuit. So here we have the controlled gates. The 0th being third qubit, We can also define arithmetic operations. I don't think they will be useful in this workshop, but sometimes they can be. So if we want to do the square root of x, defining it in a similar way as we did in Qiskit, and appending our circuit with the gate that we just created, using it on qubit number 1. Next, we're printing the circuit. Alright, so let's use all these things that we just learned to do the next task, where we need to create a quantum circuit with 10 qubits, then apply the Hadamard gate to all qubits, apply the NOT gate to qubit 0, which will be controlled by qubits 1 to 9, and next apply the Hadamard gate to all qubits again. And finally, we draw a circuit. We'll have 5 minutes for this task again. I see that people have finished. And if you haven't, remember to please mark the little moon icon or the icon with the clock. But for now, we can write the code. Importing circ, then importing the Hadamard gate and the NOT gate. Next, creating the list of our qubits. Using the range, which is fairly convenient. Next, we need to apply the Hadamard gate to each qubit. So we're using the on each function and unpacking the list. So for that to be on each of the qubits, we actually need to give each of the qubits as arguments here. And that's what we're doing. Next, we have to apply the NOT gate to qubit 0, which is controlled by qubits 1 to 9. So we need to append. First of all, we're doing the NOT gate with the target being the 0th qubit using the controlled by function. And then unpacking the list. And here we are omitting the 1. We're omitting the 0th qubit. So we're doing it from 1 to 9. Finally, we again need to apply the Hadamard gates to all the qubits. And we want to draw our circuit. Here we go. Our Hadamards appear to be correct, as does our multi-controlled NOT. The target being the 0th qubit and 1 to 9 being the controls. That's actually, yes, that's actually very good. Yes, it definitely would simplify things. In terms of why I'm not using it here, it's because we're simplifying the notebooks as much as possible so that we can get the essence of the programming for people who also don't know how to program to be able to do the maths and then present the algorithms. But yes, you don't have to use all of these appends, but you can put everything in the constructor. It's looking a little bit more, I would say, C++-y in that way, but it's definitely shorter. Okay, let's continue. Well, we can create circuits, but they don't really do anything right now other than look nice. We need to be able to run them. So we want to run them, we want to measure them, and we want to be able to get the results statistically. First, we'll create a circuit and measure it. We're creating a list of the qubits. We're creating a circuit, applying the Hadamard gate to qubit 0, and then we're using append with the measure function, where we have to unpack all the qubits we're measuring. And then we need to say the result so that it is in the label. So again, Circ went a step further to what Qiskit does in simplifying things as much as possible so that the gates being the beads that we put on the string to create a necklace is much more direct here. Since even measuring, we're appending it and it's of the same form as, for example, gates are. Yes, and we can simulate circuits with up to 20 qubits. It's not a lot, but definitely sufficient for the vast majority of algorithms when we just want to see how they work in the most basic case. Why is there such a limit? Well, it's computationally difficult to simulate quantum operations classically. Note that we're doing a lot of operations on the states, and it's keeping a lot of tabs on what the state is constantly. It has to be able to keep track of large matrices as well. So that's my guess as to why that is. It's not like realistically you'll be able to get more than 20 qubits that are fault tolerant. Tolerant meaning they are uh, fault tolerant meaning that errors don't affect them as much or affect them little enough that we can still perform computations and they do not break all our algorithms. So the limit seems small, but it's very realistic in terms of simulation as well. So to simulate our qubits, we need to initialize the simulator. Remember about the capital letter. And then we want to simulate our circuit. So we're putting it here. And to get our samples, we need to assign it to a variable. And this variable will be the result of running the run function on our simulator. So again, we're putting a name, so samples, where we will get our samples. Then we're using the simulator. On the simulator, we're using the run function with our circuit and the number of repetitions. Finally, if we want to get the result, similarly to Qiskit as a dictionary, we print, and on the samples we run histogram with the key result that we put earlier. And here we get our results, and the notation here we learned about already, that sometimes you just put natural numbers, and the natural numbers, their binary representation is the actual result. So here 0, it will be 0, 0, and 2 will be 1, 0. And they are very close to 50% after applying Hadamard. It makes sense. If we want to obtain the state representation that we know with zeros and ones, we can do it in that way. So we're defining a function that's called bitstring with bits. And what we're returning is we're creating a string that will then run. So for this, it's an empty string, and we're using join on it. So we're joining the string of our int. So from where B is in all of the bits. So we're getting some bits. And for each of those bits, so for example, some zeros and ones, we're creating a string of the integer of this bit. And we're joining it to the string. So then, when we run counts, when we assign to counts our samples, we run histogram with the key result just as before, but then we can put something that's called default function and assign bitstring, the function that we created. It might seem cumbersome, it is, but you can write a different function here if it will suit your needs better. And then we're printing the counts, and here we have the result, just as we want them. You can also just get a list of all the measurements if you'd like, not only the histogram. And for that, we're doing the function measurements. I mean, we're putting sample and measurements, which is which will be the dictionary of the results. And then this is what we'll get. Next, here we are measuring all of our qubits, which we sometimes want, but as we saw in the previous day, sometimes we're just not measuring all of the qubits because we don't need to. So here we'll measure only the 0th qubit. Here, well, we're creating the classical register and quantum register, 2 qubits, creating a circuit, applying the gate to qubit 0, and then measuring both the qubits, and the result will be in the label. We're running the simulator, similar to what we did here. And then we're defining again the function, which you can just copy if you need it. And here we just do counts, samples histogram, getting the result, using the fold function and printing the counts. So you can just see the difference being using measure here on the 0th qubit. And if we're measuring just 1 qubit, that means we'll get just one result. So that's what it is. We're getting 1 and 0, about half of the time. Now we want to implement the circuit in task 1. We want to implement this circuit. And we want to measure all the qubits and simulate your circuit for 1000 times. And here, what I was saying, it would be nice, or like nice practice before the quizzes, if you just think about what the result will be and then confirm it with the measurement that you will make. And we'll take 5 minutes again. I will start writing the task 3, and for repetition's sake, I will write everything again. So first, again, we're creating our list. Thank you, but we want 10 of them. Creating a circuit. Opening a circuit with the Hadamard gate. Applying C0 in a slightly different way.
We don't see what you're writing now, you know.
Oh, okay, thank you. That's what I was writing. So C0, Q list of 0, and then Q list of I, and then since we want to do it for I, we can use the for loop inside here. We're going to measure. We need to unpack our list and use the key here, which will name result. Let's create a simulator. Now, we'll have a variable samples where we store the result of running the simulator on our circuit with 1000 repetitions. Next, I'm just copying this function. Just to have the result in bit form, not as an integer. With the same label here, and using the false function, bit string that we defined. Finally, we'll print the counts to see our results. So now it seems that what we got. Let's see the circuit again. So we had the Hadamard here. So Hadamard will put our qubit in a superposition where we'll have 50% chance of having 0 as the result after measurement and 50% of getting 1. And so when we use the C0, it's as if the result of it is, well, stored somewhere that we don't have access to. So it will be the same for all of those. So if we have 0, the controls won't change anything, and all of these will be zero since they are automatically initialized as zeros. And if it will be 1, it will change the state of each of the qubits to 1 as well. So this is why we have only zeros or only ones as a result. And just very nicely, the perfect 50-50. Now, if you want to debug the circuits or if you want to cheat a little bit, cheat the rules of physics, then we can see the state, the current state, because we're in a simulator, not using a real quantum computer. For that, we will be importing agent measure, creating our registers, creating our circuit, applying the Hadamard gate to qubit 0, and then using the simulation. So we'll have results, and we on our simulator, we run simulate, and we'll simulate the circuit. And so finally, we'll print the results. We want to do it before measurement because otherwise it will be the collapse superposition where either get 0 or 1. So measurement, we got 2 measurements. Qubit, we have 1 qubit. If we had more, it would be here after the comma. Our output vector is the plus state, this being 1 divided by the square root of 2. We don't have any global phase, and our output vector for now is empty. So we did not apply any gate on the QNickel1. We had another qubit here, but because we did not apply anything, it is by default not visible in the output. So now we can check a different circuit where we'll have 2 qubits again, but we'll also append 1 with the identity gate, which doesn't change our state in any way, to the second qubit. And so we'll simulate the results. We didn't have any measurements yet. Here it first of all says that we have 1 qubit and its output vector is the state plus, and the second qubit, since we did not do anything with it, is 0. Phase and output vector remain unchanged. Now, let's see what will happen after we measured our qubits. So we're using measurement here on a QList, using the simulating the same way and printing the results. So we have our measurements, and this is as if it was a composite state, that's the notation they're using, and the result is 1, 0. And with qubits, we have the same thing, where we have the output vectors. And again, because it's circ and not Qiskit, we just read it from the front, not the other way around. So there's another thing that is worth noting, and it is when we want more qubits. So more or equal to 4, to be exact. Then we have a different representation of our state. So we're using just 4 qubits and using the Hadamard gate on each and simulating the circuit. And so in this case, we'll just have each of our qubits and the direct notation on each of those. And our final task in this notebook is to create a quantum circuit with 4 qubits, then apply Hadamard. Can the 0707 in Okay, in Qiskit, there is a thing where you can just use the LaTeX as output and then it will print it nicely. In Circ, I don't know. When you will be doing the task, I'll check and let you know. But I agree, I would also prefer it to be more exact than that. But the task, we need to apply the Hadamard gate to each qubit and the control Z gate to qubits 0 and 1. We use the simulator, please don't measure the circuit, and check the entries which have a negative sign. Some people are still working on the solution, so we'll have more time. But in the meantime, I can answer the question about having the exact number in our output. Well, the problem here being that I think you might notice if you work with Circ more that it is very simplified, sometimes to the detriment. And things like this, usually you have to program around yourself. In this case, well, the values are computed, like inside the simulator, the values will be computed numerically. And that's why they will be approximated and then they are stored as floating point numbers. So in that case, using circ functions that are built in, no, you cannot do that. But you could possibly do it with, for example, SymPy, which is a library in Python where you can use symbolic mathematics. It's more computationally heavy. Yes, I think so. That circ is using NumPy. So yes, or you can define it yourself, basically using a symbol for square root of 2, so that then you can display it, but I know it's a lot of work you'd have to do. For our needs and purposes, we will know what state it is, since we will deal with very simple examples where we'll know that when we apply a Hadamard to state 0, we get an equal superposition with the amplitude 1 divided by the square root of 2. And so we'll see from the approximation that this is what it is. Let us go back. We have imported circ, Hadamard gate, and the controlled Z gate. First, we're doing the same thing we've been doing, which is creating our list. We're creating our circuit. We're applying the Hadamard gate. Controlled Z gate. Here the order does not matter, but we need to specify both of the qubits. Using our simulator, so from circ, we have our simulator. We want to store the results inside of our variable called results, aptly named. We're going to simulate our circuit and print the results. Okay. So our qubits 0 and 1 will form an output vector that will be an equal superposition of all the possible states, but with the exemption of the last state here. And that's because the controlled Z gate, it will change, because we have 1, 1 here, it will change the phase of this specific state, giving us the minus here. So we're changing the relative phase. And then if we're checking just the qubits 2 and 3, since we only applied Hadamard on them, this is the plus state on both of them. Similarly to Qiskit, we can obtain our unitary matrix representation, which might be useful if you're doing custom gates and want to see how they work. So for that, we're, for example, defining the square root of 2x, square root of x again, and we're printing circ. On it, we're just using the function unitary and specifying the gate. So for the CNOT gate, it doesn't change anything unless it's in that quadrant, and in that case, it's a NOT gate. So here, it's an identity gate. Here, it's a NOT gate. So this is intuitive if you compare it to the same unitary matrix representation in Qiskit. Well, it is not in fact the same because of the Qiskit order. So here it's easier to see. And the unitary matrix representation of the C root of X gate as well is here. Now, we'll have the unitary matrix representation of the Hadamard operator on 2 qubits. And for that, we'll also simply use the unitary function again. And what you can see here is, first of all, if you remember, the Hadamard gate also has a minus in it, and hence the minus is here. And the halves are because of the equal superposition and because of there being 2 qubits. So we're getting 1/4. Okay, so that's it for this notebook. We will take a 10-minute break, and after that we'll revise the Grover's algorithm, which will be a preparation for tomorrow. So see you all in 10 minutes, so at 8:50. We can proceed to our revision of Grover's algorithm. So this is an algorithm that's usually, at least for me, fairly hard to explain to people who don't know what quantum computing is, and it should be fairly easy to explain it to you with your current knowledge. Since if I tell a person that doesn't know about quantum computing that when I'm searching for an element in a database that has a certain property, and in the worst case scenario, I can do it faster than just O of n, I'm usually met with skepticism. But if I tell you that we're using an equal superposition on our states and then modifying these states in conjunction, then I think for us it becomes a bit clearer. Because in general, so we have some pieces of paper and they are blank except for some elements which are marked with a marker, let's say like a red dot. And then you shuffle them on the other side so you don't see the marked elements. And you say to find the marked elements. So mark the elements with the red dot. And well, what the classical computers have to do, well, there's a few different ways of doing it. But for simplification, let's say there's one marked element. There's no other property. So in worst case, you'd have to do it in n times. I mean, the nth time would find it. But here we'll be using the oracle again. And the oracle will tell us whether the element is marked or not. So the problem, to be more exact, is that we have 2 to the nth elements in a list, so we're marking it as n. And for simplification's sake, one of the elements is marked. And now we're supposing that we have an oracle, which is the function f, with domain L. We don't have to worry about that. And it has some properties, which is very simple. Its value is 1 if x is marked and 0 if x is not marked. And for this function f, we want to find the element where the function has the value 1. Now, the Grover search algorithm works in iterations. And one iteration doesn't guarantee us the correct result. And more, and it's still probabilistic. It's not exactly like the algorithms we've seen where we have 100% chance of succeeding. But you can drive the chance to very close to 0. And one of the iterations of Grover's algorithm will have 2 steps. First, the query oracle operator. So what it will do is it will flip the amplitude. So if you imagine it's something that was in bronze, but if you have the amplitudes of different states, etc., the query oracle operator, what it will do, it will flip the marked state. And next, so that's the first step. The second step is inversion. And it applies something that we'll discuss later, but it's called the diffusion matrix. To perform an inversion about the mean, which will amplify the probability of the marked element. And the way it works is we'll have these elements. There's more elements here and they're all positive. So the mean will be over 0 somewhere. And so we're flipping it over the mean. So since we're flipping this over the mean here, this will get amplified. Maybe let's have this now. And if you have it here, it will be, I'm talking about this state now. And this state, which is even closer to the mean. So as you can see, our marked element is getting amplified. And why do we have to do this amplification? Because this will be the global phase. We'll not observe an actual difference if we measure here. Because it will, this and this here will have the same result in measurement. So we don't actually know. But here, if we're increasing one of the amplitudes, that means that we have a higher chance of observing it, or of observing the state that it belongs to. Okay, if at any point you have questions, ask them, but sometimes I might refer you to the QBronze section with Grover's algorithm. But I think it should be enough this revision for you. Let's look at the circuit that we have. So here, we're putting the states in an equal superposition. And this will be our iteration. Oracle being a query to f of x. And Grover's diffusion operator we can name D. We'll talk about later. And we can make as many of those iterations as possible, although there is definitely diminishing returns in using more of these iterations. And of course, we want to have a computational cost, which is as low as possible. And here we're measuring. So here we'll have the oracle and the diffusion operator, and they will be applied. So the iteration number is this, which is optimal. N is the size of the search space, and K will be the number of marked elements. In our case, it's 1. First, we'll do initialization. So we're bringing the equal superposition of all qubits. So we're implementing this step first. And we are supposed to create a 4-qubit circuit, named circuit, and apply the Hadamard gate on each qubit. And we want to see the circuit, and finally print the state. Again, please try to see whether you guess the state before finding out what it is, and it should be easy enough. And 5 minutes for that task. Alright, let's write the first step of our algorithm. And for that, first we need to create the circuit. For qubits. We're appending it with Hadamard gates. On each of our qubits. So we say qubits, but it's a list, so we need to unpick. Then we're supposed to display our circuit. And then there's the simulation. Okay. And we have what we want. So Hadamard gates on each of the qubits. We didn't make any measurements yet. And each of our qubits is in the plus state. So all of our qubits are in an equal superposition of 4 qubits. And the amplitudes, of course, make sense because if you square them and sum them up, we get 1. Let's go back to OneNote. So we can talk about an oracle that we'll be designing. So let's take a simple example of state 1111. And marking it will mean changing the sign of the state as per the first step of an iteration of Grover's algorithm. And we want to leave other states unchanged. And with that, the controlled Z gate comes to our rescue, or rather just the Z gate. So that's the Z operator, and it will change the state 0, the state 1 into state -1. So if we have a superposition on a qubit and we apply Z, will it change the global phase or the relative phase? Would anyone have an idea? So it have alpha 0 because beta 1. We're applying the Z gate. So it will change similarly to this. So if it's in a state 1, it will turn it to minus. And here I hope you can see that this is relative phase. Okay. And just the Z gate alone, if we apply to the third qubit, it will change the state that we wanted to minus. But what we don't know, it will also change the state. For example, 0011, since we have two ones here. So we don't want that. And so we can make a multi-controlled Z gate. So that for all the possible outcomes, all the possible states that we have, we'll only mark the element that we want, which is 1111. So yes, Z gate is activated on the third qubit when the other qubits are in state 1. So now we'll see how to implement a multiple controlled gate. We'll use circ Z on qubit 3, which will be controlled by qubit 0, 1, and 3. So you can see we're putting it on this. So if we have states 1, 1, 1, then it will change it to 1 as well. Or rather, it will apply it the Z gate, meaning it will be minus here. You can write it differently as well. You can also just use the unpacking the list if you'd prefer that. Here we can already see something which is, I think, an important thing to note. So we were looking at the black box so far of some unitary operation F, which was our oracle. And we didn't really look into how it worked. We just assumed or believed that it's possible to implement it. And it is possible to implement it. But as you can see, it can be pretty hard because you need to know a lot about the state that you want and then do a lot of work to actually design it. So it's pretty hard to design, which is one of the drawbacks of Oracle-based algorithms. And now to say something more about multi-controlled gates. When we'll use the gate many times on different collections of qubits, we can define a multi-controlled gate ourselves. So, for example, triple controlled Z and triple controlled X will be Z controlled by 3 qubits and X controlled by 3 qubits. And then we can append it using our unpacked list. So I think this should prove in handy later. And for triple controlled Z, the target qubit is not distinguished here. So that's why I was not saying that like the first CR controls less is the target. And it acts in the same way independently of the chosen target qubit. As you can remember, control Z can be also marked as just because of that. Okay. So if we have an operator like this, which is controlled by multiple qubits, it is not the same as several single qubits controls. And we can see an example of why that is. And we'll compare unitary matrices. I think I will switch so that we can see the result. what we're doing is creating our circuits. We're appending the circuits with the multiple control Z. And again, Z gate controlled by qubit 0. And appending Z again. Because we're doing the triple control Z. The circuit has, as far as I know, I'm sure you can use matplotlib to display it. Whether it's easy to do, I don't know. I honestly don't work a lot in Circ. I find Qiskit to be much more versatile, but because of that, again, when we'll be doing a task, I'll just tell you an answer later. But let's compare the matrices of what doing is first of all doing the controlled Z on both qubits just in one line and doing it separately. And we want to see if they're the same. And so we can see the difference. Okay, you can see the difference, for example, in signs, if you look at it, in value sometimes. So there are differences to be noticed here. That's just, you don't need to remember it or just know exactly why that is. But it's important to know that it's not the same. The multi-controlled gates have a specific quality that's important to us. Yes, and the former has the -1 here, and here we have a 1, which is one of the differences. Now we'll be doing a little bit of mathematics. After a task. So we remember the inversion about the mean, which is the second step in an iteration of Grover's algorithm. And it amplifies the amplitudes. So it basically amplifies the possibility that we get the correct result. And it has this unitary matrix. It has all these elements are the same because we have all our elements in an equal superposition. And that's the inversion about the mean. We'll see more about how that works and how else we can describe that in a moment. So N here, the big N is the dimension of the matrix. And we know how to implement this operator. We'll see why it's implemented like this. So first we do Hadamard's. You'll see a lot in quantum algorithms where we put Hadamard first. We put all our states in an equal superposition, then work on this superposition. So we're using quantum properties and then using the Hadamards again to bring them to the final states. And here we're using knots. So after the Hadamard and the knot, we're applying the multi-control Z. And now we want to create our next step in the algorithm. So we want to create a 3-qubit register. And we want to design the Grover diffusion operator that we have above here. And we want to see its matrix by printing circ unitary. So see you in 5 minutes. All right. Essentially, to answer the question, as I was saying, no, there is not an option like that. Of course, it's possible because you can just import matplotlib and do it yourself. But again, then we're going outside of the framework. So if you're doing more work in Circuit, then I think it might be useful to use pyplot from matplotlib. I think we'll wait 2 more minutes or until all the moons change into a full moon. I will start writing the algorithm. There will be a lot of writing here. Three-qubit register. Creating a circuit. And then we'll just write Hadamard. On each of our qubits. So let's unpack the list. Not. You can see the circuit here of what I'm doing. Also on each of the qubits. Now, the controlled Z gate. So it will be Z on Q2. And it will be controlled by qubit 0 and qubit 1. And next, we're doing the same thing, just in reverse order. So NOT gates on each of the qubits and Hadamard gates on each of the qubits. Next, we'll print the circuit. Now, we have to... So what do we have to do? So we need to print the circuit and its matrix by using unitary. So let's see. We managed to have what we wanted. That's the controlled Z gate. And now this might be a little bit hard to read. But just compare the first two elements. So they're different. Specifically, we have minus 1/4 here, and 3/4 here. And the numbers with the imaginary number are also different. But if you compare the next line, it's similar. But now we get the 0.75 here. Next, we get the 0.75 further. So what you can see is that the different elements are on the diagonal. And so on the diagonal, it will be so it will be 1 minus 2n. Why minus 1 minus 2n? Because this is the representation that we're doing. Identity minus 2n. That's not only circ notation. You can see it in different places as well. And you have only adds because it doesn't matter where you put it on. Because it will flip the face of the 1 qubit as well, anyway. So you don't have to put controls and targets specifically for that gate. For other gates, of course, you have to. Yeah, so one for the diagonal. And so that's why you have the 3/4. And outer diagonal, it will be -2 divided by n. So that's the representation. And we'll already have our next task, which is our last task for today. But after that, I'll go through some more mathematics. All right, so we'll do a 4-qubit register this time. And we'll have a simplified oracle. First, we'll initialize our circuit. We'll apply the oracle and the diffusion operator. So we'll make an iteration of Grover's algorithm. And it will be about 4 pi 2 to the 4th square root of that divided by 4, and that's about 3. And that's again because we want to find the optimal way where it's before the drop-off point for increasing the number of iterations. And the state 1111 should be measured way more often for us to consider the algorithm as working. So what we want to do here is we already have a lot of code written for us, which is nice. We have to write the oracle and we have to write the Grover's diffusion. So basically both of the steps of an iteration of Grover's algorithm. And we're working on 4 qubits. You can use the code from previous tasks and then you can just analyze what you got. I think we can have 7 minutes for that, looking at the previous tasks. And here in this task, we'll be using yield, which is a Pythonic way to just, let's say, throw out what we calculated into the air, and then the circuit will catch it. So just as we're doing those calculations, we'll be putting those beads onto our circuit. And so both in your oracle and in the grower diffusion function, please use yield for the rest of the code to work. The question in chat is a very good one of why there is a drop-off point where we're increasing the number of iterations, but our probability of observing the state decreases. And there is no simple answer. I will send an article after the workshop, which we should end fairly soon. A scientific article that explains it, but in simpler terms, I need to spend much more time for it. So for now, we just know that that's a thing. And for explanation, I will give it after the workshop in the form of an article. Let's write the code. So for the oracle here, we will yield a control Z, which will be controlled by a list of qubits 3, so from 0 to 3. And here what we need to add is what we did on previous task. So it will be similar to this. But that's not needed since we're yielding it anyway. But this is essentially what we're doing. So let's have the controlled Z-gate. And this will be exactly the same. And then we're doing it in reverse order. So X and the Hadamard gate. C21. In Oracle, the bracket of Z. Okay, thank you. Yeah, I'll just check. So we have this second one. Is it? Are you saying here? Oh, right, of course. Thank you. Let me see again. Oh, right, because I copied the line. We have what we want. So let's analyze the measurements. So again, what we want is the state 1111. So measurement output. Well, let's see, first of all, what we did later. So for each of this qubit, we're appending the oracle and we're appending the diffusion operator. And so this is the number of iterations. And finally, we're measuring all the qubits into the result. We're running it 1000 times. So let's see. We observed 1111 969 times. And look at the drop off from 969 to the second most common result, which is 0110, where we only get 5. So the probability of measuring 1111 is about 97%. And the probability of not measuring 1111 is very low. Whether that level of accuracy satisfies you, that depends on what you want to do with it. Like, for example, if you want, let's say quantum computers are more popular and one is searching in a database for an element, and then that element can be checked manually for having a certain quality, for example. But if we want to calculate something for, let's say, medical machines, where the output will immediately do something else, then sometimes that's the margin of error here is still too large. Okay, now let's go to the final part. Okay. So we have implemented a very simple oracle, and then we're implement harder oracles, because I said that designing an oracle is hard, but you might think that it's just a multi-controlled Z gate. In other cases, we have to think a bit more when the problem is more complicated, and we will see it tomorrow. Now, why do we use these gates specifically? What is nice about quantum computing is when you calculate the states, very often you can just see from them very clearly what you have to do in terms of the circuit. So, the diffusion operator T can be expressed in a more concise way, which is 2, and then this can be called a projection or a density matrix if you're from a physics background. Minus I, it sounds maybe scary, but remember that those are only vectors and you can calculate them as vectors. And U here is Hadamard n times on a 0 vector. And we have, this is a equal superposition. And we want to denote 0n by 0. And I would like you to see what is going on to calculate d for n equals 3. And there will be 5 minutes for that. we can calculate D. So just to have everything here, D is equal to 2 cat U bra minus identity, and U is equal to Hadamard, like 3 times in the state 0, 0, 0. We can write it differently as the tensor product of Hadamard applied to state 0 3 times. Now let's see what will happen. Here we'll get the states plus, so we'll get 1 divided by 2 0 plus 1, and we'll get it in each of those. So all these will have this representation. And with the tensor product, it will work a bit like just multiplication with parentheses. So we'll have to multiply each by each. And in the end, we'll get 1 divided by the square root of 8, since each of those will have the 1 divided by the square root of 2. And the equal superposition. There's 8, so is all of them. And now I think I'll need more space. So let's remember that bra of U, in that case, will be 1 divided by the square root of 8, and then why once? Because you can see the vectors as basically booleans telling us whether this specific state is in the superposition. So this is marked 0, 0, 0, and then it goes in this exact order until 1, 1, 1. And all the ones because all of them are in our superposition. And if we take the ket of the same thing, it will just be a column vector. That's the only difference. So in the end, we get 1, 8, since we'll squared. And we'll get all ones in here. With n equal 8. And now, since 8 is 2 to the third, and that's 2 to the n. And if we multiply it twice by 2, we'll have 1/4. So essentially, I wanted to show this because this is exactly this here. I don't think we need to calculate the 2 and the identity. But if you are calculating it, you should get the same result. Now, often in algorithms, we can just make our lives easier a little bit. So in this case, we'll implement -d instead of d. And, well, yeah, we'll just have operators that differ by the global phase, so it will have the same probabilities. Yes, that's just the property of global phase that we discussed previously. So let's see how we can express -d. So it will be minus, well, that's d. Let's apply the minus, so it will be just identity, and the minus will get in front of the doubled density matrix. And then here we'll just represent it according to the definition. And according to the definition, this will be U, and this is U. So if we have a situation where we have just the tensor product of an operator and the state, and we're doing a BRA of it, then we're flipping both of them, as if we were doing a mirror reflection. So now what can we get? We can just, since Hadamard gate has the property that Hadamard applied to Hadamard is identity, then Hadamard times n applied to Hadamard times n will also cancel out. So that's the thing that we're doing here. Now we have Hadamards that we can bring in front of the parentheses, and that's what we're doing. And so what we get is a Hadamard and the other Hadamard at state. And since this is multiplied or tensored from the right side, we'll put it onto the right side. And now we have these things. And here we have singled out Hadamards. So this is easy. We'll just have to put Hadamard gates. But here we need to still figure out what will happen. So let's see what will happen when we apply this operator to an arbitrary state, state x. So if we apply to x, then, well, x times identity will be x. We're subtracting 2 times the zeros and then x again. And since we have a situation of 0, x, we just write it as 0x. And now, if x is equal to just zeros, then the inner product, this is the inner product of zeros. Well, okay. This is the bra, meaning it will be this kind of vector, and it will have 1 here and some zeros here. And then we're multiplying it by the ket. So normal rules of multiplication. This we're adding. And what we get is 1, always. And since we get 1 here, then this expression can be simplified. since we know that x is equal to 0. And similarly, we know that 0 and 0 here, linear product is equal to 1. So we end up with 0 minus 2 zeros, and that's minus 0. So look that the sign changed. If x is not equal to 0, then a 0 vector with any x will be equal to 0. And so, in that case, we can simplify it similarly. Here's 0, so it just cancels. 2x. And so, look at what is happening. So, this state 0 is flipped. Any other state is not flipped. Since the state 0 is flipped, if all our qubits are in state 1, then we'll use a multi-controlled Z so that we flip the amplitude. But we don't have that. And so we need to apply the multi-controlled Z when all the qubits are in state 0. And so because of that, we want all the qubits in state 1. This is why here we're applying the NOT gates. And later the controlled Z gate, which is responsible for flipping the 0th element. All right, this is the end. Are there any questions? Tomorrow will be the final day of our workshop. We'll be learning about every problem that we learned here is real, but let's say a problem with more applications that is more common across computer science and mathematics, and using Grover's algorithm to solve it. So we'll have to design an oracle specifically for this problem. We'll do some graph theory as well. And this will be the culmination of our workshop. So today is another homework that you can do if you want the certificate. Oh, by the way, this section here will not be obligatory for the quizzes. If something is written as optional in the notebooks, it means that you won't see it in the quizzes or assignments. All right. Any suggestion for tomorrow's topic? Okay. So for Grovers, I think we're prepared. I will be explaining graphs from 0, basically. But if you have not heard of them, then you might want to just read something. I think on Wikipedia even will be sufficient, just so that you are familiar in any way. But otherwise, I think we will go through everything together and it should be all right. Okay, thank you very much for today. I will end the recording. I will send the article, of course. And see you tomorrow.
Thank you.
Thank you.
Very much.